Hi all, Alex B here with another question on electric power from chapter 25 of Giancali's Physics for Scientists and Engineers. This one tells us that we have an axon, which is moving sodium ions into itself at some known rate across some known potential, and asks us to find the power used by these sodium ion pumps such that we get this inflow of ions. So for this, we go back to our equation for electric power. P equals IV. And now we rewrite the current I in terms of a few other things. We can write our current I in terms of Q, the charge of our carriers, R, the flow rate of these carriers, times A, the area across which they're moving. And we need to multiply all of this by V, still the potential which they're flowing through. We know that Q, the charge of these carriers, is just the charge of one sodium ion, which is positive one charge constant, 1.6 times 10 to the minus 19 coulombs. We know that R, the flow rate, is given to us as 3 times 10 to the minus 7 moles per meter squared times second. Which we then need to multiply by Avogadro's number, 6.02 times 10 to the 23 per mole. It's the number of things in a mole. A, the area of this axon, is going to be the same as the area of a cylinder, pi times d times L, where d and L are given to us in the problem as 20 microns, so 20 times 10 to the minus 6 meters, and 10 centimeters, so 0.1 meters. And the final thing we need to know, V, is the potential which they're moving across, which we're given as 30 millivolts, or 30 times 10 to the minus 3 volts. Plugging all this in, we should find that the power P is just going to be 5.4 times 10 to the minus 9 watts, which is the power needed for these sodium ion pumps to pump in this rate of sodium ions. And here we've rounded this to two significant figures because that's the number